the resistors first. What are these resistors? What are the features of these resistors? First of all, it is a non-dynamic or not a dynamic component. What does this mean? It means that it is an algebraic component. Whatever is there, the input comes at the output at that instant, at every instant, instant by instant. There is no history, there is no memory. It cannot remember the past states or the past values. And further, the most important functional property of the resistor is that it has to dissipate. It is lossy, and most of the dissipation occurs as heat. So, let us try to characterize the resistors. In fact, most of the components generally we characterize by the IV characteristic. We put the V voltage on the x axis, I on the y axis. So, here in this particular diagram, V is the independent axis and I is the dependent axis. So, in this IV characteristic, we plot the character of the resistor, as you see here, is a straight line, and the slope in this case is I by V is 1 by R, or 1 by the resistance value. So, this is how the resistance is described. So, if you see here in this graph, if this line representing the resistor is aligned along the vertical axis, that is the y axis, then the slope is infinite, which means that R is 0, and this would represent short circuit. On the other hand, if this resistor line is aligned along the V axis, that is the x axis, then R is infinite as the slope is 0, slope of this line is 0. So, we see that the resistor line can vary from short circuit along the vertical axis to open circuit along the horizontal axis, and in between it can take any value from 0 to open circuit. This is the VI characteristic of a resistor, of a simple resistor. Now, coming back to this VI characteristic, let us take a point on the voltage axis and then draw a line directly up onto the resistor characteristic line, and from that intersection point we draw another line which intersects the current. So, at this point we see that voltage here gets multiplied by the slope 1 by R and results in the current. So, you have the voltage multiplied by this resistor resulting in this current. That becomes the governing equation for the resistor. I equals voltage by R, or it can also be written as voltage equals current into R. It is basically the same equation which is algebraically represented in a slightly different way. This is called the Ohm's law, one of the most fundamental laws in electrical engineering which you will be using almost throughout your life. Another important character in the resistor is its power dissipation, because we said that energy is going to get lost in the resistor as heat. We need to quantify how much amount of this energy gets lost. Power in watts is equal to voltage in volts into current in amps. So, VR is the voltage across the resistance and I is the current through the resistance. So, the product of this V into I will give you the wattage or the power that gets dissipated in this resistance. Now, this IV itself we saw by Ohm's law can be written as I into R, current into R, and into a further component of current which is equal to I square R. So, the equation for the power is I square R. The power dissipation can also be written as VR, and IR can be written as VR by R, as we saw earlier in the governing equations. This gives VR square by R, that is voltage square by R. So, summarizing, we see that the power dissipation in a resistor can either be I square R if you know the current, or if you know the voltage across the resistance, then it is V square by R. So, you see here the summarization of the power. Power is VR into IR. Power dissipated in the resistor is also I square R. Power dissipated in the resistor is also V square by R, depending upon which variables are known at any given point of time. There are different types of resistors. One is the carbon composition resistor. The way it is made, you have the metal film resistor, wire wound resistors and such, and many more types.